The RZ-T2H, with its multiple cores, requires communication between them. This requirement can be met using OpenAMP. This video introduces OpenAMP to demonstrate how interprocessor communication is handled within a single device. Here are the abbreviations and terms you'll see in this video. In the first part, you will be introduced to OpenAMP. OpenAMP stands for Open Asymmetric Multiprocessing. It is a framework designed to enable communication and resource management between multiple processors in a heterogeneous system. Here are two main use cases. First, it supports running multiple different operating systems on a multi-core device. Second, it enables interprocessor communication within a single device. OpenAMP has two main benefits, which are interprocessor communication and shared memory management. OpenAMP is to facilitate communication between different processors in a heterogeneous system. This is crucial for systems where different processors need to work together and exchange information to complete tasks efficiently. OpenAMP helps manage shared memory, allowing multiple processors to access and use common memory spaces. This is essential for coordinating tasks and ensuring data consistency across different processors. First, we'll introduce the master processor, which is responsible for starting up the system and managing its resources. Next, we have the remote processor. This can be any type of processor, from processors to field programmable gate arrays, FPGA, and is managed by the OpenAMP framework. Moving on, we have interprocessor communication. This allows for flexible data exchange between the different processors using various protocols. Next, we have shared memory. This is a special area where both the master processor and remote processor can access and share data. Finally, we have master memory and remote memory. The master processor and remote processor have their own dedicated memory space, respectively. OpenAMP works with many operating systems, giving you flexibility, so you can choose the ones that best suit your needs. With OpenAMP, developers can build flexible embedded systems using a variety of processors to meet specific needs. OpenAMP is composed of multiple components, including interprocessor interrupts, or IPs, which are used to signal events between processors. For example, when one processor receives data, it sends an interrupt to notify the other processor that the data has arrived. The next component is the channel. This is a two-way street between the master and remote processors, identified by its name and addresses. Next, we have endpoint. Think of them as specific addresses on a communication channel. Each endpoint has its own unique location. Next, remote processor messaging uses VirtIO, a standardized virtualized I/O device interface. It leverages shared memory to transport data. Finally, libmetal acts as an intermediary between OpenAMP and the operating system. It provides basic service like locking and mechanisms that control access to shared resources, ensuring that only one processor or thread can access a resource at a time, other services like interrupts, and memory handling. In the second part, you will be introduced to how to implement core-to-core communication. First, we will explain how the processors can communicate through OpenAMP. The communication between the processors, including the master processor and remote processor, is provided by the remote processor messaging component of OpenAMP. Remote processor enables efficient interprocessor communication by establishing communication channels and ensuring synchronized data exchange. Through standardized protocols and interfaces, master processor and remote processor can exchange data and messages, facilitating collaborative processing and task coordination. Second, we will explain how OpenAMP can manage shared memory between processors. To begin with shared memory, we set up a shared memory area that both the master processor and the remote processor can access. It's equipped with special sections for messages and has built-in controls to keep data accurate and error-free. The first component of shared memory is the shared memory region. Shared memory region is contiguous block of memory allocated in the system's address space that is accessible by both the master processor and the remote processor. In the second component of shared memory, we have a specific section called the message buffer where messages or data are written and read. It typically includes buffers for both sending and receiving messages. Next, we have the third component called the ring buffer, often used to manage the communication between processors. It consists of a circular buffer where the producer writes data and the consumer reads data. The last component of shared memory is control structures. These structures help manage the state and synchronization between processors. They may include flags or semaphores to indicate whether data is available, and metadata like buffer pointers or sizes. Next, let's look at an example using a diagram to illustrate the process of data transmission between the master processor and the remote processor. We will now provide an overview of the block diagram. First, we have the master processor, typically running a high-level operating system like Linux. Then there's the remote processor, often using a real-time operating system or running directly on the hardware. Next, we have shared memory, a space accessible to both processors. Finally, the interrupt controller unit is responsible for sending signals between them. The initial step in the communication process between the master processor and remote processor is to initialize and write data in the master processor. During initialization, the shared memory and communication infrastructure are set up. The master processor allocates a portion of shared memory and configures the communication channels, enabling data exchange with the remote processor. Once the initialization is complete, the master processor writes data to the designated area in the shared memory. After writing the data, the master processor triggers an interrupt, notifying the remote processor that new data is available. Next is the process of reading data from the shared memory by the remote processor. The remote processor reads the data from the shared memory upon receiving the interrupt and processes it. Finally, the remote processor uses the interrupt mechanism to send an acknowledgement to the master processor, signaling that the data has been processed.